Okay, so today we're going to continue with our lecture on simple linear regression. We'll do a couple more or three more problems in this chapter, because I understand that towards the end of last session, when we were talking about this 13.4, towards the end that because we were kind of running out of time, I was kind of a little bit rushed in terms of addressing this number 9 item, which is determining if the model that may have been determined as significant, if we said significant, the next step is to determine if the chosen model, and in this case, the chosen model was linear like this. We want to make sure that the linear model does indeed fit the data, okay? So to answer that question, we do what is known as analysis of residuals, which is basically looking at the residuals, which are the difference between the fitted value, okay, whatever the y hat is for a given x, and how far that is from the actual observed y. So, when you have, say, in this example, how many data? We have 25 observations. So you will have 25 such residuals that you plot. So the plot of residuals that we obtained was over here, okay? And in Excel, the data analysis module in Excel can do this for you automatically. All right. Unfortunately, the template, while it provides you more information than what Excel's data analysis can, the template does not do the analysis of residual plots. Okay, so we'll look at an example applying this analysis of residuals, and then how we interpret the analysis of residuals so that we can determine if the model, the linear model, actually fit the data. Okay, so I'm going to start with let's start with this one, 1348, okay? So let's look at that, and we will do this particular problem following these steps in regression analysis that is found in one of the worksheets. Okay, so we'll start by, again, identifying the response variable, identifying the predictor variable, and then we will create a scatter plot using the insert option in Excel, and then we will conduct the regression and correlation analysis, meaning we will ask Excel to compute this table here, which will be the basis of our analysis. All right, so let's apply that to 1348. Emily decides to buy a fuel-efficient used car. Here are several vehicles she is considering with the estimated cost to purchase and the age of the vehicle. All right, so in this sentence, we once again see a couple of variables that are declared. One variable is the estimated cost to purchase, and the other is the age of variable. And we see these two variables where the data for each of them were collected. So the data consists of how many observations, how many cars are there? 2, 4, 6, 8, 10, 12, 14 different cars. And for each car, estimated cost is provided, as well as the age of the car. So you can say that these are not new cars. So we identify which of these two variables is the variable of interest, meaning which one is the variable that we will assign symbol y. So in this case, they're really interested in estimating the cost. So this would be the response variable, y, and such that the age will be the predictor variable. So if we, in the end, were able to develop a linear model that maybe says something like this, the cost of the car, which is this is y, is equal to a plus b times the age of the car. So this is the predictor variable. So we will develop a linear model that will allow us to compute the y-intercept as well as the slope of this linear model. Okay? So we've identified the response variable. Here, the response variable is cost of the vehicle, or purchase cost of the vehicle. And then its classification is quantitative. And then the independent variable is the age of the vehicle, which is also quantitative. So referring back to our matrix table, we know that if x and y are both quantitative, then the appropriate procedure is known as the regression and correlation analysis. Okay? So when it gets down to number 4, regression equation, we can run the data analysis and then regression. All right. But before we do that, once again, when you have XY pairs of data, it is best to generate a scatter plot so that we can have an initial indication or estimation of the probable model or relationship, if there is one, between the two variables. Okay, so here's the data. We're going to create a scatter plot based on this data. So we highlight the X variable first, and then pressing the control key, highlight the Y or dependent variable. And then we select insert, and we will select the XY scatter plot, and we'll select this first one. All right, so here's the rough sort of representation of the variables age and cost. And last time in exercise 1340, I showed you how to change, to make your graph more complete in terms of detail, where you identify the title of the graph as well as identify the Y and the X-axis. But I'm not going to do that now in the interest of time. So if you want to learn how to do that again, you can always go back to the recorded session on 13.40, where I show the process for changing the labels of a graph. So based on this scatter plot, we can really readily see that there appears to be, somewhat a negative association between the cost of the vehicle and its age. So in fact, maybe this relationship can be approximated by a linear model. Okay? So for this graph, we can actually, instead of drawing the line, we can ask Excel to, we're going to ask Excel to superimpose the trend line. And the trend line that we're going to use is linear. And we will select the equation as well as the R-squared value on the graph. So here's what you see. Let me delete this Let's see if I can delete the yellow. All right. So here's your graph. Here's your equation, as well as the r-squared value. Okay, so at this point, we can tell that the coefficient of determination, or the r-squared value, is 0.67.63, which means that, let's see, all right, we can go down here. Number 6, how much variation in the response variable, meaning how much variation in the cost of a car, can be explained by its age. So here we will be using the r-squared value, and this r-squared value is equal to 0.6763, or we will say that about 67.63% of the variation in a vehicle's purchase cost can be explained by age. Okay, again, the percent of variation in the cost, the purchase cost of a vehicle based on its age is about, we can just run this up to about 68%. Okay, we can also say that about 32% of the variation in the purchase cost of vehicle is not explained by age. Okay, so we can also use this. Let me copy that, see if I can copy that and paste that here. Oops, that was just copied the plot. That we can answer this question by using this, right? So the equation says that purchase cost is equal to 18,000 is the y-intercept. Okay, $18,000, 358 minus. Okay, so look at the slope of this line here. So the slope is 1,533.6 h. All right, meaning as for each year, additional year that a vehicle gets older, its estimated purchase cost will decline by about $1,533.6 per year on average. Okay, I'm going to stress the word on average here because some vehicles vehicles purchase value may be changing per year less than this amount, and some may be a little bit more than this amount. But altogether, on average, the decline in the cost of a vehicle is about $1,534. Okay, again, that's on an average basis. Are we clear so far? Good? All right, thank you. So number 5, how strong is the correlation between the response variable and the predictor variable? So for this, to answer this question, we will use the R value, or the coefficient, the correlation coefficient, which is, the correlation coefficient is not explicitly stated in the graph, but we can obtain that from the square root of the r-squared value, which is the square root of 0.6763 is about 0.82. All right, now this one, you would want to express this as a value between -1 and +1. Now, Am I missing something in here? What am I missing?
Should be a negative because we have a negative slope.
Correct. So make sure that you apply the correct sign. And as Doug says, the correlation coefficient must be negative because the graph, the equation as well as the graph show a negative correlation between purchase cost and age. Now, what if you were asked, how would you describe, what word or words will you describe the strength of the association between the cost of the vehicle and its age? When I
Strong
say
and negative?
what, Chris?
Strong and negative?
Strong and negative. Okay, so yeah, you would want to refer to this chart. This figure here. So 0.8 is somewhere over here. All right, which is strong and negative correlation. Good. So we'll say the strong and negative correlation between purchase cost and age of a vehicle. Right? Now, number 7, it says, is the slope of the regression equation significantly different from 0? So this is the slope test where we state that the slope of the model or the linear model is 0. Translation, the model is not significant. Okay. Or alternately, H1, the slope is, let's see, what can I use here? This and this, not equal to, okay? Or you can simply say not equal to, probably less confusing, 0. And when H1 is true, the translation of that is that the model is not, is significant. Okay? And for us to make a conclusion, to render a conclusion on the slope test, we will have to run the regression, ANOVA regression. Okay, so I'm going to do that here. We'll select data analysis, regression, click OK, and then we identify the Y range. The Y is the cost, right? And identify the X range would be age. And I included the labels in the ranges for X and Y, so make sure that that is selected. And then the output range, let's put the output somewhere down here, 023. And then let's also do the residual plots, and as well as a normal probability plot, so we can do, after we do the significance test, we will do the residuals test for the appropriateness of the model. Click OK. All right, so here's the output. Okay. So for this output, again, you can see the R, the coefficient of determination, which we obtained earlier, and then same thing with the R squared. But for the slope test over here, we will say that we will reject the null hypothesis if p-value that is associated with the slope is less than alpha. Okay, so that is the decision rule. I'm just going to insert a new row here. Okay, where's the p-value? Well, the p-value in the output associated with the slope is over here. Okay, and which should be the same as the significance of f. So you can use either one. So the p-value is 0.00031, which is, and even if we set the alpha at 0.01, you will still reject the null hypothesis. This problem does not give us the the significance of 0.1 based on the significance level, based on this number compared to this number. Then we will conclude reject the null hypothesis. Okay? Translation, when you reject the null hypothesis, the linear model is significant, meaning the actual slope of the model is a non-zero number. In fact, in this case, the actual slope of the model, is negative. Okay, we good so far? So at this point, we have determined that the linear model, and what's the linear model? Here it is. This particular model is significant. So the next step is to determine if over here, number 9, is the linear model appropriate for this data? Okay, so let's go down here and then we'll go back to number 8 and number 9 after we answer this appropriateness test. So for the appropriateness, I'm just going to copy the assumptions so I don't have to retype these. All right. So the assumptions are associated with the error terms are normally distributed. Again, for this one, if you want to see if the error terms are normally distributed, we will use the normal probability plot, which is somewhere, I think, a little bit difficult to see. Let me make this smaller so I can find where the residual plots. So here they are. Okay, so I'm going to copy this and move this closer to the analysis of residuals. Okay, so for the first assumption, the error terms are normally distributed. We will be using this normal probability plot. And what we want to see in this plot is a fairly straight line, which in this case it is. So we will say that the normality assumption is met. Okay? Then we will have to test this constant variance or independence. Normally they come hand in hand. So for these two assumptions, we will be using this residual plot. All right. What we want to see is that one, the plot is random, meaning no pattern. And 2, that residuals can be or are confined inside two parallel lines. Okay, so in this case, we can say that the plots are random and also can be confined into parallel lines. So these three assumptions are met. Okay. Because these assumptions are met, we will conclude that the linear model that we tested to be significant is appropriate. Okay? So once a model is deemed appropriate, then and only then should we be doing this kind of analysis using the model. Okay, so the model can be used for two things. One is for estimating the actual slope of the equation, and number two is for estimating the value of y, the value of the response variable, either using a point estimate or an interval estimate. So in this problem, the linear model, was the linear model, this linear model here, we have determined to be both significant and appropriate. Okay? So because of that, we can answer question number 8. Question number 8, let me make this bigger. Okay, for question 8, it says for each unit change in the independent variable, age, by how many units on average is y, the cost of vehicle, changing? Okay, we answered that question already. It is $1,533.6. All right. Now, this
Okay.
1,000, yes.
Do we put a negative for that change?
Yeah, you can do that. To be more, well, depends really, because it says for every unit change in the independent variable, it doesn't say whether plus, increase or decrease.
Yeah, I just
Okay.
wanted to clarify so
Yeah.
we don't get confused on an exam.
Right. So what you would want to say, if the question was phrased here as, for every year a car gets older, by how much does it purchase cost change?
Okay, that makes sense.
That, if it's phrased that way, then you can say, decrease by $1,534. Right?
Okay, thank you.
Okay, you're welcome. So this is, we call this the point estimate of B, which is the actual slope of the model, of the linear model. All right? And so the question number 9 says, hey, if this is only the point estimate, give me the 95% interval estimate of the true change in y. Give me the true change in the cost of a vehicle for every year change in vehicle age. So here, we don't have to compute that because that is reflected in the output. over here. Okay. So we copy that. So let's explain this. So the interpretation of this number is that the interval for every year a vehicle gets older, the true decrease in its value is between $866 and $2,201. Does that make sense? Yep. Okay. So I hope the explanation of the analysis of residual is clearer this time than last time. Okay. So what we've done here so far for 8 and 9 is this. We used the model for estimating the actual slope of the equation. All right. Now we develop a model. The other reason why we develop a model is so that we can estimate the true value of the response variable, such as this. Okay. So let's now add something to this problem. And let's put, say, number, let me move this number 10 down here. And let me make this, instead of use the model for estimation. Suppose that, oh, let me leave it like that. So here's a question where we will be using the model for estimation. Suppose that Doug is selling his 10-year-old Mercedes. Oh, no, you're not BMW, right, Doug?
That's right. Get it right. We don't do Mercedes.
Okay. All right. Chris wants to buy it from him. The question is, how much, let's say, using the model that we just developed, how much will Chris or Doug offer, or Chris will pay for the car? Okay, so at this point, I'm going to be asking, let's see, who's here today? Stella, okay, thank you.
Would you just multiply for every year that it ages, it goes down $1,533.
Okay.
So would you multiply that by 10 and then just subtract the 10-year decline in the amount of money from the $18,358?
That's correct. So essentially, what Stella, if you allow me to restate your answer.
Yes, of course.
Just substitute 10 into the variable age, right? So you were just saying multiply the age by the decline per year, and then subtract that from the 18,000. So you have 18,358 plus 1,533.6 times 10. Okay, did I, translate your answer?
Yes, you
accurately?
did.
Okay, thank you. So this is what we call as the point estimate.
What was that supposed to be? Adding or subtracting?
Subtracting. Oh, thank you. Good catch. Thank you. So Doug's car is now only valued at 3,000. Doug, are you willing to sell your car to Chris for 3,000?
Sounds good to me.
I can guarantee you the blue book's higher than that.
Yeah. This data is probably an old
But
data.
Chris will like the price.
Yeah, of
Yeah, it works for
course.
me.
All right, so this is called the point estimate. But the true range of value for Doug's car is actually could be, lower than 3,000 or can be higher than 3,000 because there are other variables that we're not considering here, right? Like maybe his car has, some features that would add value to the car. So the other way of estimating the value of y is using what we call as the interval estimate. Okay. Now for the interval estimate, there are two kinds. The first kind is known as the prediction interval estimate, and the other is known as the confidence interval estimate. Okay, there's a subtle but important difference between these two. The prediction interval estimate is used when you want to estimate the true value of y given x. Oops, correct the spelling there. Whereas the confidence interval estimate, you use this when you want to estimate the true average value of y given x. We should delete that. Okay. Now, prediction interval estimate is used when you want to estimate the true value of, let's put this, say, 1y given x. Whereas the confidence interval estimate is of estimating the true average of a group of y's given x. So if you were trying to estimate, the interval estimate of Doug's car, since there's only one case here that you are interested in, then we will be using the prediction interval estimate. On the other hand, if you are interested in, say, you have a group of, I'm stressing the word group, a group of, say, 20 cars who are all 10 years old, all right? The average value or the average cost of those cars is somewhere between, this confidence interval estimate. Okay, again, this is used when you have only one y, whereas this is the confidence interval estimate is you have a group of y's given x. Does that make a difference? I mean, does that make make sense? So, Excel will not compute this or this for you. When I say Excel will not compute that for you, the data analysis module in Excel, that the output will not give that to you. All right. Your book will show you a way to compute the Y, but that's using a very lengthy formula. Since we are avoiding manual computations at this point, we can use, so this is now where I will introduce the use of the template. Because the advantage of using this template, especially this simple linear regression template, the advantage of this is that it will also compute for you down at the bottom here. It will compute the point estimate, your Y hat, and also compute the prediction interval estimate as well as the confidence interval estimate. Okay? So let's see how this car example can be used, or let's see how we can use this template in that car example. So I'm going to do, let's see, what does it say? Pay attention to the comment. It says, enter in this column the data for the independent variable. Okay? And then enter in this column the data for the response variable, or the value for Y. So I'm going to copy the data from here. Copy that. And then I'll paste that over here. Note that this template, excuse me, gives you the equation, right? As well as the R squared value, the R value, the P value of F. And then don't worry about the Durbin-Watson statistic here. You will not be responsible for that. But just kind of briefly, Durbin-Watson statistic is used to determine whether or not the error terms are independent. Okay, but typically you can use an analysis of residuals to answer this question. Okay, so are we clear so far in terms of what the output shows? The advantage of the output is that it gives you it picks the important numbers, like the coefficient of codetermination, the correlation coefficient, the significance of the F value, which you can use for the significance of the model test. Down here, make this bigger. We have the ANOVA output, which is similar to what the Excel output had. All right, so look at these numbers here. The interval estimate of the true slope. So down here is we can input the value of X. So Doug's car is 10 years old. Okay, so here you go. The point estimate is 3021. And when we computed that by hand, that was, what was the value? Okay. Slight difference because of this one is rounded. The decimals are rounded. But what actually Chris will pay Doug is somewhere between, as high as 11,000. Okay, I'm using the prediction interval estimate here because we're only talking about one car. So Obviously, the lower limit is a number that is not practical, right? So this is actually the lower limit would be set at 0. But Doug would not be that, gullible to sell the car for free, right?
That's right.
So, but Chris can pay as much as 11,000 for the car. Does that make sense? All right. Now this number here is the interval estimate for the true average price of a car, of a 10-year-old car. If you have a group of 10-year-old cars, you'll say that the average selling price of those 10 cars is somewhere between 0, so we'll bring it up to the lowest possible value again, and $6,732. Okay? So, does that make sense? We're good? All right. So let's move on to the next problem. We're done with that. How about this problem? Oh, I thought I had the numbers for this. I must have deleted those.
I have them on my copy of it.
Yeah, I know. I had it earlier. I must have deleted those by accident. Let me open the other. Let me open another. Let me see. Okay. Hey, Doug. I think we can. Let's see. Do you want to try this one? Explain this, since you have a copy. I'll
No,
give you the floor.
that's okay.
Come on, Doug, you can do it.
Can't catch me by surprise like that. I'll freak out on you.
Okay, that's not fair, huh? Let me save this as different files. So before I, there you go. This is what you have, Doug?
That's what I have.
All right, good. So I'll just, all right, and then I'll resave this onto the original file. Okay. So a sample of 12 homes sold last week in St. Paul, Minnesota is selected. Can we conclude that as the size of the home, and reported below in thousands of square feet, increases, the selling price, reported in thousands, also increases? Okay, so here's the data. Do you want to, let's use the template to make this quicker, all right? So I'm going to copy this group of observations, go to the template, paste that onto here, and delete this extraneous information. So there you go. The template already created the equation for us. Price and size, also size is in what? Thousands of also. Now look at the plot. It's not showing anything. How come? What do I need to do? Can we just edit the, which one should we edit? The size is for the highest is 1.5. All right, but look at the highest here, it's 8. So we can adjust the scaling of the x-axis to, let's make that Okay, I reset it, so it made automatic. And there you go. So here's the plot of these 12 observations. Now tell me, so we kind of skipped a few things here, but let's go back here. Let's answer a few things. What is the response variable? Alan? Oh, I think I called him already. Nick? Are you there, Nick?
Yeah, I'm here.
So what's the response variable in this problem?
That'd be the home size.
No, it's the other one. The selling, you're interested in estimating the selling price. Okay?
Okay, got it. Thank you.
Yeah, qualitative. Now, so make sure that you guys know that for the test, okay? Because I will be asking the same set of questions, similar set of questions when we do problems involving regression and correlation analysis. Oh, not qualitative. All right, how about the independent variable? Megan?
Is it the home size?
Okay. Home size, and this is quantitative or qualitative?
Quantitative.
Uh-huh. Okay, good. And the appropriate testing procedure, Hannah?
Is it the same one as last time, the linear?
Yeah, regression
Yeah, that one.
and correlation. Uh-huh. Okay. And what is the regression equation? We'll have to pick it up from here. So I can probably just copy and paste. All right, so the regression equation would be that price is equal to 67.18 plus 25.641 size. Number 5, how strong is the correlation between the response variable and the independent variable? Give me a number. Shania?
Yeah, 9.4%.
That's not the answer. That 9.4 is over here.
Okay, sorry, I've been in the car this whole time, so I haven't been able to follow along super well.
Okay, no
Is
problem.
it plain R?
All right. Yeah, so just the R, which is 0.3072. Okay. What's the word or at least a description that we can attach to this strength of correlation? 0.3 is somewhere over here. Okay. So that would be weak, but positive correlation. Why did I say positive correlation, Doug?
Okay,
No, your mic is
get
off.
my button in time. It's a positive slope.
I keep surprising you. So what description or why? Why did we say positive?
Oh, because it's a positive slope.
All right. Okay, good. Now, number 7. Is the slope of the regression equation significantly different from 0? Let's copy the hypothesis we have over here. Copy this too. Oh, before I do that, I need to insert a couple of lines. Okay. Oh, I meant to do that here. One more. Okay. So here's the setup for the slope test and the decision rule. Reject HFP values less than alpha. What is our conclusion? Look at your p-value.
.3314.
Yeah, huh? So what is the conclusion? Is the null hypothesis rejected? P-value is 0.3314. And an alpha, did the problem state the alpha? It doesn't say it, but we can even if you set it an alpha of 0.1, the conclusion would still be the same, right? This is the correct conclusion?
Yeah.
Is this relationship true? Is 0.33 less than 0.1?
No, it's greater.
Okay, so therefore, the conclusion would be to fail to reject HO. And then by failing to reject the null hypothesis, we will say that the linear model is not significant. Meaning this model really is not a good predictor for the selling price of homes. Okay? So because we are concluding that the model is not significant, then we really cannot be doing this kind of analysis here. Does that make sense? We don't even have to test for appropriateness because, first of all, the regression model, based on the data that we have, this is not a useful model. Because it is not a useful model, do not use for estimation. Okay? Are we clear?
Renee, can you explain a little bit more why it's not useful?
Okay, sure. Okay, all right, so we go back to this slope test, right? The slope test says that the slope of the equation is 0, meaning there is no relationship between x and y. So the translation of of the null hypothesis is that this slope is equal to 0. So whatever the x value is, it really has no bearing on the value of y. The decision rule would be to reject the null hypothesis if the p-value associated with the sample data is less than the significance level. And we determined the p-value to be 0.3314. That's based on here, right? And compared to a significance level of 0.1, you know, this relationship is not true. It's false, right? Because it is false, we will fail to reject HO. In other words, you know, this pretty much is based on the data that we have, we cannot reject this null hypothesis. Does that make sense?
Yes, thank you.
Okay, you're welcome. Okay, so in working this problem, I'm going to use Excel's data analysis module just because I want to generate the residual plots right away. So we can determine right away if the chosen linear model is appropriate or not. Okay. So here we have a manufacturer of small electric motors that uses an automatic milling machine to produce the slots in the shafts of the motors. A batch of shaft is run and then checked. All shafts in the batch that do not meet required dimensional tolerances are discarded. So this is kind of a quality assurance situation where you know, we're going to see is in this as explained in the second paragraph. At the beginning of each new batch, the milling machine is readjusted since its cutter head wears slightly during production of the batch. The manufacturer is trying to pick an optimal batch size. So this would be the batch size. But in order to do this, he or she must know how the size of the batch affects the number of defective shafts that are produced in the batch. Okay? 30 batches were inspected, so you have the 30 observations here. And the number of defectives in each batch was counted. So if produce a batch size of 100 units, they observe 5 defective items. They produce another batch of 125 items, they observe 10. So these are the sample XY pairs of observations. We want to know, you know, or at least this manufacturer wants to know if, you know, not if, but how. They know that there's a cause and effect here. The larger the batch size, you know, this cutter, the cutter head obviously will wear out, right? As the batch size gets larger. But understanding how the size of the batch affects the number of defective shafts in the batch is important, especially when you're running a particular batch. The question is, how many defective units will that produce? Before we can answer this question, we have to first establish this relationship between X and Y. Okay, so we're going to run a regression analysis to answer that question. And once again, we will subject this, you know, whatever the resulting linear equation is, through significance test and appropriateness test. All right, let's do this. We'll highlight batch size and then highlight defects. So at this point, I'm just generating the scatter plot. Select this option. All right, here's your scatter plot of batch size and defects. Okay, now it's quite obvious here that this relationship is a little bit curved, meaning nonlinear. All right. Now, just so that we can explain this process of testing a significance and then testing the appropriateness of a model, let's superimpose, or at least let's develop a linear model instead of a non-linear model. Okay, so I'm going to run a regression, insert data analysis, regression, click OK, and then the input y range would be defects, and then input x range. Right? And I included the labels. Output, let's put the output somewhere in, say, E21. And then I'm going to have Excel compute the residuals as well as the normal probability plots. All right. Okay, we'll analyze those later. But look at the resulting statistics. Look at the R value. How would you, what words would you describe the resulting R value?
Strong and positive.
Not only strong, but close to 9.
Perfect.
Not perfect. Well, perfect would be 1.0.
Almost perfect.
Well, yeah. So instead of just saying strong, we will say there is a very strong correlation between batch size and the effects produced. Right? That's an interpretation of that number. How about the R squared value? Let's convert that into percent. So we would say that 95% of 95.3% of the variation in defect can be explained by batch size. Okay, that makes sense because if you look at the, this plot here, it's a very pronounced relationship, right? Now, how significant is the, so if we did the slope test, if we do this, what's the p-value? Here's your p-value, or that. There's like 0.0, and then how many zeros? 20 zeros before you start getting a, a number. So the p-value is almost 0. So even if you set your alpha at 0.01, you will still reject the null hypothesis and conclude that the model is significant. But is the linear model appropriate? To answer this question, we'll use the plots, the residual plots. Let me copy this and move them down over closer to the plots. Okay. So as far as the normal probability plot goes, that's fairly, straight right there. But as far as the residual goes, what do we want to see here? Do we want to see random, as well as all the points can be confined within two parallel lines? Now, this is definitely not a random pattern, right? So based on this, we will say that the independence or constant variance assumptions are not met. Because they are not met, we will conclude that the linear model is not appropriate. And it's quite obvious. Yeah, it is quite obvious in the plot here. All right, so let's see what model is more appropriate. I'm going to right click on that and then add trend line. Now observe, I should make this a little bit bigger so you can see the resulting numbers. Okay. Now for the linear, what was the R squared for the linear? Over here, right? For the linear model. Let's superimpose. Let's try different models. Let's see exponential. Does exponential fit? Let me see this. Obviously not, right? How about logarithmic? Let me remove the linear line there. So it always puts the linear. So logarithmic? Nope, not either, right? How about the polynomial? Second order. So let's delete that. Does it look more like a fit?
That looks nice.
All right. So maybe we can ask Excel to give us the equation that describes that polynomial relationship. Second order. Let's display the equation on the chart and display the R squared value on the chart. I'm going to remove this extra line so we can see. All right, do you guys recognize this equation here from your algebra class? Isn't this?
It looks like a quadratic equation.
That's right.
Isn't it ax squared plus bx plus c?
Uh-huh.
Okay.
Yeah, so that is expressed like a plus bx plus cx squared. Correct. Otherwise known as the quadratic equation. So look at the R squared value. 0.9954. Compare that to the R squared value of the linear model. Obviously, this one is better, right? Correct? Yes. Okay,
Correct.
so let's run this model using the data. So instead of, we determined that this model is not appropriate, okay? But this one is. So let us construct a quadratic model, because this kind of connects us to the next chapter. Let's run a quadratic model and then test that model both for significance and appropriateness. So this model will require variable x and then additionally x squared. Note that in our original data, we have only x of, but not x squared. But that's not a problem because we can always create the x squared data based on x. Okay, meaning using the values of x here, square each one, then you have the x squared value. Now that's what you see in this next worksheet, where I have already computed this was the original data, and this is the x squared values. So this one, 10,000, it's just this squared. Okay, that's a formula. So once you create the formula there, you copy that down, then you have the new variable that you can run in your regression analysis. Is that clear so far? We just created this new variable based on this column. Okay, so we will be able to develop a quadratic model expressed as Chris said, using this format. So we will ask Excel to compute A, B, and C using the usual regression steps. Okay, so let's do that. Data analysis, regression, click OK, and input Y range. That would be defects. Come on. Not letting me pick this. All right, I'm just going to force it to, I'll just type the range for Y. That would be B4 all the way down to B34.
I was running into that problem too after this latest Windows update. It seemed to make a mess of things.
Right. Yeah, if you recall, one time when we were in class last term, when we run a regression, and but anyway, that's probably something that this class will just confuse them. So let's just. All right. So X, the input X range would be from C4 to D34. And then I included the labels in declaring the ranges. And the output, we'll put the output in maybe F4. And we'll also do the residuals as well as the normal probability plots. Okay, okay. It would not allow me to do that. Let me see if I can recreate those data in a new worksheet. Okay, so defects, I'm going to move this to the left side. And batch, this is just a name, all right? Batch squared. And the formula there would be this squared. Okay, and then I'm going to run, hopefully this will work this time. Data analysis, regression, and all right. For some reason, there's something defective in this worksheet here. Okay, labels included. Output would be in E4. And then I'll ask Excel to compute the residual plots and normal probability plot. Click OK. Here's the output. Oh.
So Renee,
Yep.
I just wanted to, just for the class, does everybody understand why he selected both columns for the Y this time?
Not Y, for X.
For X, excuse me.
Yeah, meaning this one here. Because this one is your X. This is the X squared. Okay? So these two columns are the two predictor variables. Okay, so this was the number we obtained earlier. So the linear model, the quadratic model, can be written this way. Y is equal to 6.89. Let me just type this up. It's probably easier that way. So we will say defects, that's Y, is equal to 6.897. That's the Y-intercept. And then the slope of batch size, the slope of X, is negative, right? It's negative 0.12 batch, or X, plus, this is a positive slope or coefficient, 0.0095. I'm just rounding up. Batch squared. So this is what we call the quadratic model. Is this model significant? Answer is absolutely yes. Why? Look at the p-value. It's almost zero. It's not going to be zero. Almost zero. Okay. Next question. Is it appropriate? Answer? Well, let's look at this slopes, the residual plots. Fairly straight line. Everything will be, you don't see any pattern. Okay. So based on these plots, we will say that the quadratic model is appropriate. So if you were asked to, if you were asked to estimate the number of defects that will be produced by a batch size of, say, 200, how many defects are expected? So let's compute this number here. So to compute the expected number of defects using the quadratic model, we will apply this model and into batch you simply substitute 200. Okay, so let's apply that formula here. Equals 6.897 minus 0.12 times 200. Or if you want, instead of saying 200, let's pick that up here. Okay, K10 plus 0.0095 times K10 raised to the power 2. So if, oh, that can't be. Is something wrong with my, here's my mistake. I have one, this should be 3 zeros, right? So the formula here should also say 3 zeros. That's my mistake there. So you'd say that in a batch size of 200, you would expect 20 or 21 defective units. Okay? But if somebody says, let's run a batch size of 400, how many defective units are we going to expect? Well, let's just replace that cell with 400. And here we go. That's your number of defective units. Okay, now I'm doing this kind of estimation because we have determined that this quadratic model is both significant and, more importantly, it is appropriate. But by using these residual plots. And also, we can see that from, the original plot. The quadratic model fits the data set. Questions?
So we're only going to know to do the quadratic formula based on around the graphs.
Shoshana, was that you?
Yeah.
You were the audio was kind of coming off towards the end. What was that? We're going to use the quadratic.
So if we mess around with the graphs lines, where it matches up, That's the only way we'll know to use the quadratic formula.
The only way to know the quadratic formula would be to see if the model fits the data. I mean, you have to test the model. And we knew that if we try to superimpose the linear model through the data set, okay, and make that thicker. So obviously, the linear model does not fit in this example, but the quadratic model does.
So I think part of your question, Shoshana, is yes, you do have to kind of play with those to see which one is a better fit, but you don't know for sure until you test it.
Okay, and
Yes.
that's using the Excel.
Yeah, the residuals, correct. Because the template will not generate this residual plots for you.
Okay, thank you guys.
Mm-hmm.